Enter the quantum realm, classical versus quantum, the ultimate divide. Imagine you're holding a baseball. You throw it. Pretty straightforward, right? You can guess its path, where it'll land, how fast it's moving. Now, what if I told you that very same ball, if you could shrink it down smaller than a single atom, could actually be in multiple places at once? And that just looking at it would fundamentally change where it is? Sounds like something out of a sci-fi movie, doesn't it? But guess what? It's the real science of our universe. The everyday world you see around you, the solid objects, the predictable events. That's just one side of the story. Get ready to journey across what we're calling the ultimate divide, from the reality we think we know, into the bizarre, mind-bending, and utterly fundamental world of quantum mechanics. What if everything solid isn't quite as it seems? Section 1. The classical world, our everyday reality. For centuries, the way we understood the universe was through what we now call classical physics. Think of big names like Isaac Newton. His laws of motion and gravity described a universe that worked like a giant, predictable clock. If you know the starting conditions of an object, its position, its speed, the forces acting on it, you can predict its future with amazing accuracy. Throwing a ball, launching a rocket, figuring out the orbits of planets. Classical physics nails this stuff. It's intuitive and it's deterministic, meaning everything follows a clear cause and effect path. Objects have definite properties. A car is in one specific spot, moving at one specific speed. And energy? It can be any value, like smoothly turning the dial on an old radio. This is the world our senses pick up, the macroscopic world we live in every day. There's a certain comfort in its predictability. It just makes sense. But as scientists started digging deeper, right down to the very fabric of matter, they found that this comfortable predictability, well, it shatters. Section 2. The quantum leap, a whole new ballgame. As the 20th century kicked off, new experiments started giving results that classical physics just couldn't explain. Things like black body radiation, that's how hot objects glow, and the photoelectric effect, light literally knocking electrons off metal, just didn't play by the old rules. It became obvious that down at the atomic and subatomic level, the world of electrons, photons, and all the tiny building blocks of everything, a completely new set of rules was in charge. And this isn't just about things being super tiny. It's a fundamental shift in how reality itself actually works. So welcome to the quantum realm. It's a place where our everyday intuition isn't just challenged, it's flipped completely on its head. We're talking about a world governed by probability, not certainty. A world where particles can be waves, and waves can be particles. A world where the simple act of looking changes what you see. This is that ultimate divide we're here to explore. Section 3. Key difference: determinism versus probability, the universe's casino. One of the biggest, most mind-bending differences is all about prediction. Classical physics, like we said, is deterministic. Think of it like a cosmic game of pool. If you know exactly how the cue ball, your initial conditions, hits the other balls, the particles, you can calculate precisely where every single one will end up. No guesswork involved. But then quantum mechanics strolls in and says, hold on a second. At the quantum level, we can't predict outcomes with absolute certainty. Instead, we have to deal in probabilities. Picture a particle, say an electron. Before we measure it, we can't pinpoint its exact location. Instead, it's described by something called a wave function, which tells us the probability of finding it in various spots. So instead of that pool ball having one definite path, it's more like it has the potential to be in many places at once, each with a certain chance. It's like a cosmic lottery, and the wave function gives you the odds for each possible outcome. Only when you actually make a measurement, when you look, does the particle decide on a definite spot. And it's not because our tools aren't good enough. It's because the universe itself, at this tiny scale, seems to run on chance. The predictable clockwork of Newton gives way to a kind of universal casino, where the dice are always rolling. Section 4. Key difference: smooth versus chunky, the energy packets. Another huge split is how energy and other properties behave. In classical physics, things are continuous. Think about that old analog radio dial again. You can turn it smoothly and land on any frequency, any volume level. Energy, speed, momentum, all these could in theory take on any value along a smooth spectrum. If you want something to have a tiny bit more energy, you just give it a tiny bit more. But quantum mechanics throws a wrench in that with a concept called quantization. This means certain properties, especially energy, can only exist in specific discrete amounts. Think tiny packets called quanta. Max Planck was the first to figure this out, realizing that energy isn't a continuous flow but comes in these little chunks. It's more like the digital volume control on your phone. You can't set it to 10.5. It's either 10 or 11 with no in-between. An electron orbiting an atom can't just have any old energy level it wants. It can only occupy specific energy levels like rungs on a ladder. To jump between these rungs, it has to absorb or emit a whole quantum of energy. A photon, for example. It can't just hang out halfway between rungs. This chunkiness of energy is a cornerstone of the quantum world, and it's totally alien to what we experience every day. Section 5, key difference. The observer effect. Does looking change reality? All right, this is where things get famously weird. In our classical everyday world, looking at something doesn't really change it. If you watch a car driving down the street, your act of observing doesn't affect its speed or direction in any significant way. You're just a passive bystander. But in the quantum realm, the act of measurement is anything but passive. It fundamentally alters the system you're measuring. Remember how we said a particle exists in a superposition of multiple possible states described by its wave function before we measure it? Well, the moment you try to measure a property, like its position, that wave function collapses, and the particle suddenly settles into one definite state. Imagine you have a magical toy that's somehow a car, a boat, and an airplane, all at the same time. But the second you look closely to see what it is, poof, it instantly becomes just a car, or just a boat. The act of observation forces it to pick one. This isn't because our measurements are clumsy and shake things up. It's an inherent feature of quantum reality. The observer isn't separate from the system. They're tangled up together. It seems the universe, at this deep level, behaves differently when it knows it's being watched. Section 6. Key difference. Wave-particle duality. An identity crisis. Classically, we like to keep things neat. Stuff is either a particle or it's a wave. A baseball is a particle, a solid, localized lump of matter. Sound or light, in the classical view, are waves. They spread out and carry energy. They have very different characteristics. Particles have definite positions, while waves are spread out and can interfere with each other, creating patterns like ripples. Quantum mechanics pretty much tosses that neat distinction out the window with something called wave-particle duality. Everything at the quantum scale, electrons, photons, even whole atoms, can act like both a wave and a particle, depending on how you set up your experiment to look at them. Light, for example, can behave like a wave, creating interference patterns just like ripples in a pond. But it also acts like a stream of tiny, discrete particles called photons, which is what Einstein showed with the photoelectric effect. An electron, which we usually think of as a tiny speck, can also behave like a wave, diffracting and interfering with itself. It's as if that baseball we talked about can sometimes act like a solid object and other times spread out like a ripple, all depending on what you're trying to measure. This dual nature is one of the most counterintuitive, yet absolutely experimentally verified parts of the quantum world. Section 7. More quantum weirdness, superposition and tunneling, and the strange rules don't stop there. Let's quickly go back to superposition. It's not just about being in multiple places at once. A quantum particle can exist in a superposition of many different states simultaneously. Different energies, different spin directions, you name it. A common analogy is a spinning coin. While it's spinning, it's neither heads nor tails. It's in a kind of blend of both. Only when it lands, when it's measured, does it settle into a definite state. Heads or tails. Another way to think about it, imagine you're trying to decide what to have for dinner. Until you actually choose, pizza, pasta, and salad are all coexisting possibilities in your mind. That's kind of like superposition for quantum particles. Then there's quantum tunneling. Classically, if a ball doesn't have enough energy to roll over a hill, it just won't make it. It's stuck on one side. But in the quantum world, a particle can sometimes pass straight through an energy barrier it shouldn't, classically speaking, be able to get over. It's like that ball suddenly appearing on the other side of the hill, even though it didn't have the oomph to roll over the top. This isn't magic. It's a natural consequence of the wave-like nature of particles. The particle's wave function doesn't just hit the barrier and stop. A tiny part of it can extend right through, meaning there's a small but real probability of finding the particle on the other side. This tunneling effect is actually super important for things like nuclear fusion happening in the sun, and even how some modern electronics work. Is your mind officially blown yet? We're really getting into the nuts and bolts of how reality itself operates, and it's definitely a wild ride. If you're finding this journey into the quantum realm as fascinating as I do me a quick favor and hit that like button. And if you haven't already, make sure to subscribe and ring that notification bell so you don't miss our next adventure into the mysteries of the universe. Your support really helps us create more content just like this. Section 8. Entanglement, spooky action at a distance. Perhaps one of the most famously bizarre and talked about quantum phenomena is entanglement. Albert Einstein famously called it spooky action at a distance. Imagine you have two quantum particles that are linked or entangled. Once they're entangled, their fates are intertwined, no matter how far apart you separate them, even if they're light years away from each other. If you measure a property of one particle, you instantly know the corresponding property of the other. A common analogy is having two special coins. You flip them, put each one in a separate box without looking, and then mail one box to the other side of the world. The moment you open your box and see, for example, heads, you instantly know the coin in the other box is tails, assuming they were set up to always be opposite. With entangled particles, it's not that they decided their states beforehand and kept them hidden. It's that their states are correlated in a way that classical physics just can't explain. Measuring one particle seems to instantaneously influence the state of its partner, faster than light could travel between them. Now, this doesn't mean we can send faster than light messages. That's a common misconception. But it does show us an incredibly deep and strange interconnectedness at the very heart of reality. Conclusion. So there you have it. On one hand, we have the classical world, predictable, intuitive, the world of our everyday experience where balls fly in smooth arcs, and energy seems to flow continuously. And on the other, we have the quantum realm, a world of probabilities, outright weirdness, where particles are also waves, exist in multiple states at once, can tunnel through barriers they shouldn't, and can be spookily connected across vast distances. This ultimate divide isn't some mistake in our theories. It seems to be a fundamental feature of our universe. Classical physics works brilliantly as an approximation for large-scale objects and everyday stuff. But it's quantum mechanics that gives us the deeper, more fundamental description of how reality actually ticks. The analogies we've used today, spinning coins, dinner choices, pool balls, and magic toys, are just that. Analogies. They help us build a little bridge of understanding. But as physicist Vlatko Vedral pointed out, quantum particles often behave in ways that have no true equivalent in our big-scale world. They're helpful starting points, but the quantum world ultimately asks us to stretch our intuition way beyond what feels familiar. The rules you thought you knew, yeah, they pretty much get flipped upside down when you step into the quantum realm. Everyday reality, it turns out, is far stranger and more wonderful than it first appears. The world we see is built on a foundation of quantum weirdness, a foundation that scientists are still working hard to fully understand, and one that powers everything from the lasers in our Blu-ray players and the computers in our pockets to the very stars shining in the sky. Thanks for joining us on this journey into the quantum realm. What quantum concept just completely blows your mind the most? Let us know down in the comments. If you want to keep exploring the amazing frontiers of science, check out some of our other videos right here. And hey, don't forget to subscribe for more explorations into the universe's biggest questions. Until next time, keep questioning everything.